Talked about how to determine the rate expression for the reaction at hand from the experimental data by estimating whether it suits the first order rate equation or whether it suits the second order rate equations, considering irreversible uh, kinetics. But let's say we want to now get the rate equations in terms of higher order, which is neither 1 nor 2, and we say that as nth order rate equation. So if we are attempting to fit the experimental data that we have to an nth order rate equation, then the form of rate equation will be given as minus Ra equals to minus dCA dt equals to k Ca to the power n. The reaction I have considered is A gives products. Okay. If you separate the terms and integrate them, then you will get the expression as Ca to the power 1 minus n minus Ca0 to the power 1 minus n equals to n minus 1 into kT. Remember, n is not equals to 1 here. If it is equivalent to 1, then obviously you can get k into Ca, which is exactly the first order rate equation. If you put n equals to 2, even then you can get the expression as obtained from here. Unless and of course you have non-elementary kinetics or where the reactants are initially present in exact stoichiometric ratio for bimolecular cases. Now this n value over here, this you can find either using trial and error method. So you have to try with different values of n. So one way of determining n is by trial and error. Okay. Another way to do that is what we say, which is used in advanced reaction engineering studies. We may like we have Ca data and we have T data, and of course we know Ca0. So what we can do is we can use this equation over here as a model equation and perform an optimization study to obtain the values of the unknown parameters like k and n together. So these are known values for us, known from experimental data, and you just perform one optimization study. By optimization study, I mean you do a general least squares of error between the experimental data and model predicted data, and you can estimate the unknown parameters k and n. This is another way to go about things, but for the sake of undergraduate courses, the general trend is to use trial and error method and find the value of n which minimizes the variation in the rate constant value or k value. Now, one interesting thing about this equation is that if n is greater than 1, then for any finite value of t, let me write it down, for any finite value of t, the reaction is incomplete. So it will never reach a point where the entire resource or the initial reactant provided is completely exhausted. So at finite time, if the value of n is greater than 1, the reaction will not go to completion. But if this n becomes less than 1, then for finite value of t, the concentration will fall to 0 at some point. And if you continue further, mathematically it will show that there is some negative value, but that is practically not possible. It's not a feasible thing. So you must remember that if the order is less than 1 for a finite time value, concentration will fall to 0, assuming this equation. So with that knowledge, we can also find that at what time the concentration of A will exactly be 0. So Ca becomes equivalent to 0 at the value of T, which is greater or equal to Ca0 to the power 1 minus n divided by 1 minus n into K. This expression is important, fairly important, especially for competitive exams. This question is often asked. I mean, you just need to put this formula and find out that at what value of time the concentration of A is completely exhausted. Okay, so the idea is that we should not continue the integration beyond this time value that we obtain from the formula given here, because otherwise the concentration, the real concentration, will actually fall below 0, and that is not practical. Okay, and because of this reason, in real life systems we observe that fractional order will shift upward towards unity as a reactant is getting exhausted. The more we reach towards the depletion of reactant, the fractional order shifts towards 1. This we will take up in details later. Right now all you need to know is that if n is less than 1, then for a finite value of time t, the reaction will reach such a state that the initial concentration is completely exhausted. Okay, so this is it for empirical rate equations of nth order. Thank you.